These are examples for section 10.3, Trigonometry. Example 1. Given triangle ABC, find all the trigonometric ratios for angle A. Then convert each ratio into a decimal rounded to 4 decimal places. Try to remember that when asked to find trig ratios, or ratios of a right triangle, that you're not solving an equation. You're simply finding a ratio, two numbers compared to each other, and sometimes putting it in or converting it to decimal form. So with that in mind, let's start with sine. Sine, S-I-N, of angle A. And by the way, sine, cosine, and tangent are always functions on the angle, one of the acute angles of the right triangle. So the sine of angle A is defined as the opposite side of that angle over the hypotenuse of the right triangle. Hypotenuse is BA here, and the opposite side was BC. And so the sine of angle A in this particular problem would be opposite 16 over hypotenuse 34. Always check to see if the ratio will simplify itself. This one does. It reduces by 2. So the sine of angle A is equal to 8/17, or 8 to 17. 8 to 17 is the trig ratio for sine of angle A. Now for the decimal equivalent, simply take 8/17 and convert it to a decimal. 8 divided by 17, use your calculator, you get approximately 0.4706, 4 decimal places. Going on to cosine, the cosine of an angle, in this case angle A, is defined as the side that's adjacent to that angle, this one right here, CA, to the hypotenuse. Once again, the hypotenuse to AB. And so the cosine of angle A is equal to 30 over 34. Again, this simplifies 30/34, so we reduce it by 2. And the cosine of angle A is 15 to 17, or 15/17. Converting to a decimal, the cosine of angle A, taking 15 and dividing it by 17, we get approximately equal to 0.8824, rounding to 4 decimal places. And finally, the tangent of an angle, in this case angle A, is always equal to the opposite side to the adjacent side, BC to AC. So this would be opposite to adjacent. So the tangent of angle A in this particular triangle would be opposite 16 to the adjacent 30. 16/30 reduces again by 2, and so the tangent of angle A is approximately equal to 0.5333, 4 decimal places. And this reduced was, let's see, that was 8/15. So we have all 3 trig ratios written as ratios, and then we have all 3 of those ratios written as decimals. Practice 1. Given triangle ABC, find all the trigonometric ratios for angle B. Then convert each ratio into a decimal rounded to 4 decimal places. Try this one on your own by pressing pause on the video. When you're ready, turn it back on and see if you were correct. Okay, for practice 1, starting with the sine of angle B. By definition, the sine is opposite over hypotenuse, so that would be 12 to 13. 12/13 does not reduce, so this is your answer for the ratio. Then finding the decimal equivalent, the sine of angle B is approximately equal to 12 divided by 13 is about 0.9231, 4 decimal places. Make sure it's 4. On to cosine, the cosine of angle B. Defined cosine is the adjacent side to that angle over the hypotenuse. So adjacent would be 5 over hypotenuse 13. 5/13 does not reduce or simplify. So this is our ratio, 5 to 13. And then our decimal equivalent, take 5 and divide by 13, approximate to 4 decimal places, and you're going to get approximately 0.3846. And finally, the tangent of angle B is defined as opposite over adjacent. So that would be 12 over 5. And this one does not reduce, and just because it's improper doesn't mean you change it to a decimal or a mixed number. Just leave it like this, just like this. And then for the decimal equivalent, the tangent of angle B, divide 12 by 5, and you get exactly 2.4, but we do need those 3 zeros on the end because we're rounding to 4 decimal places. 1, 2, 3, 4. And there are your answers. When solving right triangles using trigonometry and any of the trig ratios that we've discussed, we end up solving an equation, writing an equation and solving it. And depending on what you're doing in the particular triangle will dictate which trig ratio you end up using. So let's start with this first one. Find the length of GH, this right here, in this right triangle, rounded to the nearest tenth of a unit. Or nearest unit, ones place. Okay, so we have a right triangle here. We've got one side length, which is the hypotenuse, and we've got one angle measurement besides the right angle. So we take the angle that they give us, the acute angle they give us, angle G here. Because they gave us a numerical measurement for it, that's where we start. So you take that angle and you say, okay, I need GH. This side in relation to that angle is adjacent to it. So we're going to need a trig ratio that has adjacent in it. Well, that eliminates sine because sine is opposite over hypotenuse. Notice we have, of the 3 sides, we only have one of the sides, which is the hypotenuse. And so we're going to need the hypotenuse. We need the adjacent side and the hypotenuse. Well, that eliminates the tangent because tangent is opposite over adjacent. So just by a process of elimination, we know we're going to end up using cosine. So we write the cosine of angle G is equal to, remember, it's adjacent over hypotenuse. I'm going to go ahead and use the letters. GH is to the hypotenuse GK. So that's where you start. Then you substitute in everything that you know and solve for what you're looking for, GH. This is the cosine of angle G, and actually this is implying the measure of angle G. The measure of angle G is 36, so the cosine of 36 degrees is equal to GH, which was what we're looking for, to GK, which is 28 feet, or just 28. Now we solve this equation. What do we solve for? We solve for GH. That's what we're asked for. So we want to get GH by itself. Since GH is being divided by 28, we multiply both sides by 28. And over here, the 28's divide out, and we're left with GH. Over on this left side, we have 28 times the cosine of 36 degrees. Now, you don't have to put parentheses around this, but I do this on purpose to make a point. cosine 36 degrees or sine 58 degrees or tangent 38 degrees or whatever is all one value. You cannot split them apart. There's only one way you can split them apart, and we haven't gotten to that yet. We'll get to it later this lesson. But that means 28 is multiplied with this entire expression here, cosine 36. That's important because here in just a moment we'll do a problem where we have to move this particular thing to the other side. So, but anyway, what we have here is GH is equal to 28 times the cosine of 36 degrees. So once we evaluate this in our calculator, we will get the length of GH. Actually, it'll be an approximate length. What you do, you take your calculator and you make sure you're in degrees mode first. We went over this in our notes. You go to the degree mode, the mode key, which is right here. You key down twice, and you key over to the right once where it says degree. It's in the row that says radian degrees. We're going to use radian later on this semester, but for right now it's always degree. So you hit degree, hit enter, and clear. And now you're ready. 28, and then times, you can use parentheses or you can just put in cosine immediately, 36, close parenthesis, enter. And you see that you get approximately 22.65247584 and so forth. So we're rounding to the nearest unit, which is the ones place, so that would be the this place right here. So since this is 6, this goes up to 3. So we had gotten 22.6524, so forth. And so GH is approximately equal to 23. So GH is about 23 feet long. Now at this point, if you wanted to, since you now have this length, you could go ahead and find this length because you already have two lengths of the triangle, two sides of the triangle, and you use Pythagorean Theorem to find the third one. They didn't ask for that here, but they will in the future. Also, we could find the measure of angle K by either using another trig ratio or simply using triangle angle sum theorem. That would be the fastest way. Example 3. Find the length of MQ rounded to the nearest unit. So here's MQ right here. Happens to be the hypotenuse. So we're looking for the hypotenuse length. We're given one side length. We're given one angle, acute angle measure of a right triangle. And so let's figure out which trig ratio we're going to be using here. We obviously need the hypotenuse. So tangent is out because tangent doesn't include the hypotenuse. Since we're given the measure of angle M here, we're going to find either sine or cosine of angle M, 25 degrees. Well, we've got the opposite side length to that angle. So we need one of the trig ratios with opposite, and we need hypotenuse. Well, that would be sine. So we're going to use the sine function. The sine of angle M is equal to the opposite side, which is NQ, to the hypotenuse, which is MQ. Now substituting in everything that we know about those values, we have the sine of angle, the measure of angle M is 25 degrees, equals NQ's length is 17 meters, or 17, to MQ, which is what we're looking for. Now this time you'll notice that what we're looking for is in the denominator of the ratio. In the previous example it was up here. But we still have to solve for MQ. The first thing we need to do is we need to get MQ back up into a numerator so that we can solve for it. So I'm going to multiply both sides by MQ. You say, why do that? It's just going to cancel these out. Yes, it does, but you also, because you have to multiply the same thing on the other side, you get MQ over here. So suddenly it's in the numerator. Those divide out and you get MQ times sine 25 degrees equals 17. And we still need to get MQ by itself. MQ is being multiplied with the sine of 25 degrees. So to get rid of the sine of 25 degrees, we divide by the sine of 25 degrees. We do not divide by the sine, and we do not divide by 25 degrees. We divide by the sine of 25 degrees, the whole thing. Means we have to divide by the sine of 25 degrees on the other side to balance the equation. Those entire things divide out, and MQ is equal to 17 over sine of 25 degrees. That's the exact answer, by the way. If they ever ask you for the exact answer, they want us to round to the nearest unit. So we are going to use our calculator. MQ is approximately equal to, taking your calculator, make sure you're in degree mode. I'll do it one more time. Go to mode, go down to this third row, over to the right one, make sure you're in degrees, clear, and then you're ready to go. On this one, we have 17 divided by the sine of 25 degrees, close the parenthesis, enter. We get about 40.225426991 and so forth. We went around to the nearest unit, so that's going to be about 40 meters. So this side right here, the hypotenuse of this triangle, is about 40 meters long. And all we had was this side right here in this angle. Now let's apply a little bit what we learned to some real life situation. Example 4. The Leaning Tower of Pisa in Italy has a very noticeable tilt. If someone dropped an object from the tower at a height of 150 feet, right here, how far from the base of the tower will the object land? We're assuming there's no wind to blow it away. It comes straight down perpendicular to the ground. If that happens, we've created a right triangle with the side of the tower that's leaning and the distance straight down from where someone dropped the object and the ground. Very kind of a skinny right triangle. We're given the angle of the drop, which is 5 degrees, and we know that we did it 150 degrees up. We want to know how far out from the base that is, this right here. So I'm going to call that X for lack of a name there. So we have a right triangle. We have one side length, not two, so we can't use Pythagorean Theorem. This is not a special right triangle because this is 5 degrees, not 30, 60, or 45. So we're forced into using a trig ratio. That's how you know you're going to use a trig ratio. So we look at our triangle and we say, okay, what angle besides the right angle, which angle do I know? I know this angle right here, 5 degrees. So this angle, we're going to start here. We need this side right here, this little side of the triangle. Well, that's opposite that angle. So we need opposite, but we also are given this side of the triangle here, which is adjacent. It's not the hypotenuse, so it's the adjacent side. So we need opposite and we need adjacent. Well, that's tangent. So we use the tangent, the tangent of this angle right here, which is 5 degrees. So the tangent of 5 degrees is equal to the opposite side from that angle, which is X, over the adjacent side, which is 150. So there's our equation, an equation that would find the value of the X. Alright, at this point we need to solve for X, so we need to get rid of, since X is being divided by 150, we multiply by 150, but on both sides. The 150s over here divide out, or cancel out, and X is equal to 150 times the tangent of 5 degrees. And so now we take our calculator and calculate. Remember, we're rounding to the nearest foot. So I put in, make sure you're in degree mode. We put in 150, put in tan or tangent 5, close parenthesis, just like that, and hit enter. We get about 13.123299953 and so forth. Rounding to the nearest unit, that gives us about 13 feet that object's going to land away from the base of the Tower of Pisa. In the last two examples, you need to make sure you understand how to use the arcsine, arccosine, and arctangent functions on your calculator. We went over that in the notes. And also remember that the arc trig function is the same as saying the inverse trig function. So arcsine and like this, arcsine of an angle is the same as saying the arcsine of that angle. These mean the same thing. This is the inverse of the sine. Okay, beginning with example 5, find the measure of angle D rounded to the nearest degree. When we're literally finding the measure of an angle of a right triangle, we still use trig ratios, but in a slightly different way. Notice we've got two of the sides of the right triangle already given to us. Now we're not looking for the third side in this problem. We're looking for one of the acute angle measures. We've got the right angle, but we don't know what these two angles are, and there's no way we can tell any other way but by using trigonometry. So what we do is we start off the same way as you did on the first few examples we've done, and you say, okay, I want angle D, so I'm going to start with this angle, and I'm either going to use the sine, cosine, or tangent of angle D, but it's got to involve the two sides that they gave us that are related to this angle D, its location. So notice that opposite angle D is one of our measurements for this side of the triangle, and the hypotenuse is the other side. Remember, this is not adjacent, even though, you know, in specific terms it really is next to. But we don't refer to the hypotenuse as adjacent. We refer to it as the hypotenuse because there's only one. This would be the adjacent side. So we're going to use opposite and we're going to use hypotenuse. Which one is that? That's sine. So the sine of angle D is going to be equal to opposite side, which is FE, over the hypotenuse, which is DE. Then we substitute in what we know. This is the sine of angle D, we do not know the measure of angle D yet, equal FE, which is 48 centimeters, or 48, over DE, which is 57 centimeters, or 57. Now, we don't start solving for D, the measure of angle D yet, because we need to get this converted to a decimal. If you recall our first couple of examples, we took a trig ratio like this one, and we converted it to a decimal to 4 decimal places. That's what we're going to do with this. So anytime you have both these numbers in the ratio, you need to go ahead and find the decimal. So we're going to take our calculator like we did, similar to what we did on the first couple of examples today, and we're simply going to put in 48 divided by 57 to find the decimal equivalent. Remember, 4 decimal places, so I'm going to rewrite this as sine, the sine of angle D, is equal to, it's approximately equal to now, 0.8421 rounded to 4 decimal places right there. So at this point we need the measure of angle D. That's what we were asked for. The only way you can get the sine off the measure of angle D here, or the cosine or the tangent function, is by taking the arcsine or the arccosine or the arctan. So what we do is we take the arcsine, like that, of the left side of the equation, of the sine, and then we take the arcsine of the right side of the equation to balance it. 8, 4, 2, 1. So we're taking the arcsine of the left side of the equation, taking the arcsine of the right side of the equation. And the reason why we're doing that is because the arcsine cancels out the sine. And all we're left with is angle D, or the measure of angle D. And then over here we have the sine, the arcsine, of 0.8421. This is as close as you're going to get to the exact angle right here. Then, to find it rounded to the nearest degree, make sure you're in degree mode in your calculator, like before. And this time, we're going to push the second key, second function key, and then right above sine, you'll see the sign with the little -1 exponent. That's the arcsine. Push that, and you'll see it on your calculator. And then you put in 0.8421, close parenthesis, and enter. And so we get approximately, for the measure of angle D, we get approximately 57.36254335 and so forth. Rounding to the nearest degree, we get 57 degrees. So the measure of angle D, right here, is about 57 degrees, real close to 57 degrees. At this point, we could find the measure of angle E. All we'd have to use is the triangle angle sum theorem. Anyway, they didn't ask for that, but there's the measure of angle D. Okay, now let's apply finding the measure of an angle that we need. Example 6. An urban planner needs to know the measure of an angle formed by a street and the edge of a bike path. So here are the streets. This is a map looking down. Okay. What is the measure of angle DEG? DEG, this one right here. We're going to find that first, and then it says, what is the measure of angle DGE? We'll find that one later. What is the length of diagonal GE? It's right here. So we'll worry about those other two in a minute. Let's focus in on this first one here. Round all answers to the nearest yard. That's the ones place, once again. So let's take a look. We've got this city block. There's a diagonal here, creating a right triangle. Actually, two right triangles, but we'll use this one right here, triangle DEG. Notice that here's the right angle in the triangle. We're wanting the measure of angle DEG, this one right here. So we start with this angle. It's either going to be the sine, cosine, or tangent of angle DEG. So let's see what we have here. We don't have the hypotenuse, so we can't use that. We do have the opposite side from this angle. We also have the adjacent side to that angle. So which trig ratio is that? The tangent. So the tangent of angle DEG is equal to, and I'm going to go ahead and immediately substitute in values here. Okay, so opposite, tangent is defined as opposite over adjacent. So opposite angle E is 150 over adjacent, which is 115. Okay, we need a decimal for this. So rewrite it, the tangent of angle DEG, and then take your calculator, divide 150 divided by 115, and we get, looks like we get 1.3, about 1.3043, 4 decimal places, remember. And so, at this point, we need to find the actual measure of angle DEG, or something close to it. So we need to get rid of the tangent. How do we do that? Take the arctangent of both sides of the equation to get rid of the tangent here. I'll do it on the right side. So the arctan and the tan cancel each other out or undo each other, and we have the measure of angle DEG remaining. So now we take the inverse tangent of 1.3043. So make sure you're in degrees. That's the second key right here, tan or arctan, and then 1.3043, close parenthesis, enter. And we get about, rounding to the nearest yard, that's the ones place, you get 52.5 and so forth, so that would be 53 degrees, about 53 degrees. So this is 53 degrees here, about. Okay, so we found the angle we were looking for. Now for this next angle, what is the measure of angle DGE, this one right here? Well, this one's going to be real easy because we can use triangle angle sum theorem. We've got two of the three angles. So we have the measure of angle DGE, and I'm going to add that to 90 degrees, So this one plus this one plus the one we've already found. Now because that was approximate, we have to say it's approximately equal to 180 degrees. Now we go ahead and add these two to measure angle DGE plus, let's see, that's 143 is about 180. Then subtract 143 from both sides, and the measure of angle DGE is about 37 degrees. So we found the measure of that angle now. Finally, they want us to find the length of diagonal GE, this right here. Well, we've already got two sides of the right triangle, so we can just use Pythagorean Theorem. This was by triangle angle sum theorem. And now by Pythagorean Theorem, we can say the hypotenuse EG squared is equal to one of the legs, DE squared, or 115 squared, plus the other leg, DG squared, which is 150 squared. And so solving for EG, eventually, EG squared is equal to 115 squared. Let's see, that would be 13,225 plus 150 squared. Watch this, 15 squared is 225, and then you have two zeros, so that's 22,500. So EG squared is equal to, now we need to add those together, and we get 35,725. Now we need to take the square root to get rid of the square because we're looking for the length of EG, not EG squared. So we take the square root, and EG is approximately equal to, putting that in your calculator, the square root of 35,725. You get approximately 189 yards. 189 yards along here. And this was about 37 degrees. So we got quite a bit of information about that triangle.